Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah wa salatu wa salamu ala rasulillah amma ba'd. So lab 1 deals with MPLAB X. So under the lab 1 folder on Blackboard, you will find PIC 18 instruction set, which is a section from the data sheet which contains the instructions. Section 29. So this section is taken as a separate file for easy reference. So you can refer all the instructions here. And then you have EE366 Lab 1 slides, which explains you step by step how to use MPLAB X. And the Lab 1 PDF file. The Lab 1 PDF file is this file, which contains the examples and the activities that you have to solve for Lab 1. So each lab you will find a similar file like this, which will have a few examples and this and explanation for the activities that you have to solve for the lab. And then you have MPLAB X user guide and the video for the lab 1. The datasheet for the microcontroller is given here. You can click on this link to download the datasheet for PIC18F45K80 microcontroller.
This is the memory map of PIC microcontroller, the data memory map and the program memory map. The assembly instructions that you are going to write, they will be stored in the program memory, which is the ROM actually, and it starts from 00 location until 7FFFH. So once you write your program and download the program in PIC microcontroller, it will be stored here inside this program memory. And the data memory, it has general purpose registers and special function registers. We will be using these registers, general purpose registers, for storing some data during the program execution. These are the special function registers. We will see them in detail later on when we start using the different modules and components of PIC microcontroller. And the assembly instructions that we will be using in this lab are add LW, which adds a number to the W register, move LW, which moves a number to W register or copies the number to W register, and we will also see move W to F to copy a number from W register to a file register location, add WF, adding W register to a file register location, increment F, increment the value of a file register, or decrement the number inside a file register location. BCF, clear a bit from a file register location, or BSF, set a bit in a file register, one of the bits of a file register location, or toggle a bit, BTG, toggle one of the bits of a register. So file registers are general purpose registers or special function. They can refer to general purpose register, special function register, or the W register itself. So in place of F, you can either write location of one of the special function registers, or a general purpose register, or the W register. Now let's look at MPLAB X IDE. So once you have downloaded MPLAB X,
so when you open MPLAB X for the first time, you will see the software window like this. So click on create new project, or you can click from here file new project. Select Microchip Embedded Standalone Project. Click Next. In the device list, type PIC 18F45K80. So it will be filtered here. You can select directly. So the device or the microcontroller that we are using now is PIC 18F45K80 microcontroller. In the tool, check simulator for the time being. Click Next. For lab 1, we use the assembler. So if you have already installed XC8 compiler, so this is very important. You must install the XC8 compiler as well before we start lab 1. So MPLAB X IDE along with the XC8 compiler must be installed before we start lab 1. So the assembler is listed here as the PIC assembler. PIC is short for PIC assembler. So click here. So this is the compiler that will convert the program that we write in assembly language to the hex file or to the machine code. So select the assembler from here. Click Next. You can create a new folder with your username, or you can select the location of the project. You can type lab 1 here as the name of the project, then click Finish.
If your username in your computers, if your username is in Arabic, MPLAB X will not be able to compile your program properly. So if your username in your computers, if it is in Arabic or any of the locations here in the path of the project, if it is in Arabic or any language other than English, then it will not be able to compile properly. So in that case, you can browse and change the folder. Create a new folder under C, under C drive. Create a new folder. Click here. Create a new folder and select this folder. You'll have to do this if you have any character other than English in the path of the project. Okay, then click Finish. Now you have a new project created with the name Lab 1. Make sure this is the main. If you have multiple projects open, make sure this is the main project. So right click on it and select Set as Main Project. So it will show as bold. So if Lab 1 is not the main project, we'll have to select that and set as main project. Now it is already selected as the main project, so I have an option to unset as the main project. But if it is not the main project, you'll have to set this as the main project. Okay. Now expand source files. You don't have any source file now. Since you are opening MPLAB for the first time, you don't have any source file. So right click on source file, select new, and then click on other. Select new and click on other. From here select assembler, and on this side select assembly file.asm. So it will open an assembly file with no content, an assembler file with no content. So it will open a blank assembly file. Next, you can write a name for this. So this is lab 1 example 1. Click Finish. So you have a blank assembly file. Now let's write the first example code here. So this is the first example. So always when we write a computer program, we start writing with comments. So comments in assembly language, they are written with a semicolon. So you can write your name and you can write your number, your KAU number, your student ID number. Then you can write here which lab and which activity is it. So this is lab 1, example 1. Then you can write a brief description of what this program is about. Then we start writing our program here after the comments. So the first instruction that we have written here is a processor directive. Now all these instructions, they should be written with a tab space like this. So the comments, they start in the first column and the instructions, they are written with a tab space.
The first line here, #include xc.inc. This is a preprocessor directive. #include is a preprocessor directive. It tells the assembler to include this file xc.inc, and this file defines the structure of the microcontroller, the internal memory of the microcontroller, and the location of the special function registers, and the data memory and the program memory. Program sector is once again another processor directive which tells the starting location of the program memory. And since we have a label start here, so you write the same label here, the same label name here, start, and origin 0, org0 starts for origin. Origin 0 indicates the location of the program memory, the location of these instructions in the program memory. So as we have seen here, the program memory starts from location 0 until 7FFF. So we can store our program anywhere inside the program memory, but usually we will store our program starting from location 0. So the first instruction will be stored in location 0 and 1. Each instruction, as we have seen in the instruction set, move LW is a one-word instruction. That means it occupies 2 bytes. So each instruction in the program memory is a 16-bit instruction, is at least a 16-bit instruction. Some of these instructions are 32-bit instructions. For example, the LFSR is a 32-bit instruction. So usually these instructions, they are 16-bit instructions. That means they occupy 2 bytes in the program memory. They occupy 2 bytes in the program memory. So the first instruction, which is move LW, it will occupy location 0 and location 1 in the program memory. Similarly, the next instruction here will occupy location 2 and 3, and then the go to instruction. The go to instruction here tells the microcontroller this is like an infinite loop. So after executing these 2 instructions, the clock of the microcontroller, it keeps on running, it does not stop. So we cannot tell the microcontroller to stop executing. So it has to keep on doing some, as long as the clock is running and as long as the microcontroller is powered on, it has to keep on executing something. So after executing our program, we have to tell the microcontroller to keep on jumping to the same location. So the $sign here indicates the same location in the program memory. So the program keeps in a while loop, is in an infinite loop. It keeps on jumping to the same location without executing anything after this. And the end is again, once again, a directive to the assembler to tell the assembler that there is no more instructions after this. to assemble. So end is not an assembly instruction, it is a processor directive. It is not meant for the microcontroller itself, it is for the assembler. So the microcontroller will only execute these three instructions. It will not execute the processor directives. The processor directives are only instructions for the assembler or the programmer. The XC8 PIC Assembler User's Guide contains more information regarding the assembly instructions, regarding how to write the assembly program, how to write different data types in the assembly program, and this is also given here in one of the slides. For example, for binary numbers, we just have to write all the bits followed by capital B. For octal numbers, you have digits from 0 to 7 followed by O or Q, and for decimal numbers 0 to 9 followed by D, or if you don't write anything at the end, that will be considered as a decimal number. For hexadecimal numbers, 0x prefix or H at the end, and for ASCII numbers, the character should be enclosed in the quotation mark. And if you scroll down, you will also find the details regarding the assembly operators, the assembler directives. For example, we will be using the config directive for the configuration bits. We use the end directive at the end of the program, EQU directive, the origin directive, the program section directive, now these are the preprocessor, those were the assembler directives. Now we have the preprocessor directives here, hash define, hash include, and the other details regarding the assembler, linker, the utilities, etc. So this is a very important document that you can refer if you want to find out any more information regarding how to use the MPLAB assembler.
Then this start is simply a label. Labels are written in the first column like this without a tab space, and they should be a single word, and after the label you can write a colon to indicate that this is a label. So labels are simply names of a location in the memory. You can assign a name to a location in the program memory, and they can be used for program loops and for jumping, or to divide your program in different sections. So go to $sign is to tell the microcontroller to simply go to the same location on which this instruction is stored. So it keeps on jumping to this location. So either you can write the location number, you can write a label, you can assign a label here, you can write a label, or you can simply say like this. So it keeps on jumping to the same location. That means it keeps on executing this instruction. So this is like an infinite while loop which simply jumps to the same location. It tells the microcontroller to do not execute anything after that. And why do we need this? We need this because maybe the program memory might have some other instructions written here from the previous program execution. So it might have any other instructions stored in the program memory from the previous instruction. So we do not want microcontroller to execute any other instruction after this. So we tell the microcontroller to keep on jumping to the same location. Click on the button Build Main Project. So click on this button, build main project, or we can also click on this button or this button, which builds the main project. So it compiles or it assembles the program and it generates the machine code. So if you don't have any errors in your program, you will find build successful. If you have any error, for example, if you forget, suppose you write this instruction in the first column like this, then what happens is when you build your program, you will find a warning. You'll find a warning given here, and this warning, it says found opcode in column 1. So move LW is an opcode. It says found opcode in column 1, and if you click on it, it will take you to this line. Okay, it says found opcode in column 1. What you have to do is simply move it to the second column by pressing the tab button. Now if you build again, you'll find clean successful. You find build successful. Suppose if you have some other typing mistake or some other error in your program, for example, in this code, instead of writing it like this, if you write it in this way, then this is an error. There is no space in the go to instruction. If you write it in this way, you will find an error. It says here illegal opcode. You can find error here. It says illegal opcode 2. Okay, so always look at the errors. Whatever errors you have, first go to the first error. Go to whatever first error you have, click on this error line, and it will take you to the line where you have this error, and it says illegal opcode 2. So there is no opcode name as 2, so it should be a go to like this. Okay, same way, if you have an error here like this, then if you build your program, you will find the first error. When you have errors, then always start with the first error. The first error that you see here, it says illegal character 0. Click on it and you'll find this is the line. So in this line, what is the error? Find out what is the error. It is this one. There should not be any. So there is a spelling mistake here. So now you have everything clean, build successful. There is no error and there is no warning here. The program is built and you can find the hex file is generated. So this is the location of the hex file, which has the machine code that later on we will see how to download to the microcontroller. Now let us debug this program to see the locations, see the W register and how this data is copied to the W register. So click on debug, debug main project. Okay, you will find the debugger console is opened here and the user program is running. Now go to the variable tab here. You don't have a variable, or if you don't see the variable tab, click on window, click on debugging and select the variables tab. Okay, double click here and add WREG. Simply type WREG, click enter, and W register is added here. So you'll find when the program executes, you will find the values in the W register. So these are the debugger buttons: finish debugger or pause debugger. So what we will do is we'll pause the debugger. We'll pause the debugger and we will start executing from the beginning again. So reset, click on this button, reset. Okay, the program has moved to the first location. Okay, and then click on this button, step into. Step into will execute the instruction one by one. So now let us execute the first instruction here. So click on this button, and as soon as the first instruction is executed, you will find the value 2F. The value 2F has been copied to the W register. Can you see that? So when you click on step into once again, you will find the value 30h of 0x30 has been copied to the W register. Now if we click on it again, then it does not do anything because it is simply executing the go to instruction. Now once we have seen this, we'll stop the debugger, okay, and we will start writing the second example. Now we can also see the program memory here. So if you click on window target memory view, and you can select program memory, you can select the file registers. So this program memory map, this table that I have explained you before, is also shown here. You can find at location 0 and 01. The opcode is, or the machine code is 0E to F, and the assembly instruction move LW 0x to F. And at location 2 and 3, you have the opcode 0E30 move LW 0x30 is the assembly instruction that is stored in location 2 and 3. Similarly, the locations 4, 5 and 6, 7, 4, 5 and 6, 7, they have EF02 and F000, and together these instructions are go to location number 4, which is the same location. So go to location number 4, which is the same location. It keeps on executing this. So if you write any other instruction here after that, for example, if you write here add LW 0x05 and build the program again, and look at the program memory tab, you'll find this add LW is stored in the location number 8 and 9. But this will not be executed. The program will execute only until here, and keeps on jumping to the same location. So this will never be, add LW will never be executed unless you remove this instruction. Now let us look at the second example. So what I will do is add another source file, new. Now for the first time, you have to click on other and select the assembly file from there. Once you have already done that, you can find assembly file.asm shown here. So for the first file, for the first time, you have to click on other, select assembler, and select assembly file.asm. Click next, write the name of the program, write the name of the file, and click finish. But now, since you have already done that before, you can find it here, new assembly file.asm. You can write it like this, and we'll write lab 1 example 2, finish. Now one project cannot have two assembly files or two source files at the same time. So you can either execute this file or you can execute this file. You cannot execute both of them at the same time. So what we'll do is right click on the first file and select exclude file from current configuration. So we must exclude the first file from the current configuration, and we'll simply execute the second example now.
So this is the second example, which copies 48. Let us change the number to something like 27. Now 27 is a decimal number. And add 1, it becomes 28. And then so we copy 27 to the W register and then add LW1, that means it becomes 28. We add 1 to the existing number and then move W to F0x20, that means the result of this addition should be copied from W register to a file register location 20, that means location 20 in the data memory of PIC18F45K80 microcontroller. So once again, let's update the program here. So this is the second example. So once again, launch the debugger after building a program and go to the file registers. So let's look at the variable tab first. So when we start executing, click on the step into button. You can find this 27 is copied to W register. So this is a decimal value, decimal 27. In hex it is 1B. So when you click again, 27 became 28, and the value in hex it is 1C. Now let's look at the file register tab. So the data memory is empty, you don't have anything here. So as soon as you execute the third instruction, the answer, which is 1C will be copied to location 20. So this is location 20 in the data memory. So this is 20, then 21, 22, 23 until 2F. Then you have here 30, 31, 32 until 3F, and so on. So in this location, so look at this location when you click on the step into button once again. So 1C is copied, which is the result of the addition, is copied to the location 20. You can see it is highlighted in red that there is a change in this location. So you can stop the debugger here, and if you want to test the same program with some other values, so let's change the value here, 27, let's change it to, for example, 54, and instead of adding 1, let's add, for example, 4. So 54 plus 4, and move W to F, and let us change the location to 35. So if you make any change in your assembly program, you'll have to build the program once again. So once again, build your program. So you can find build successful, the program is built, and then launch the debugger once again after that, and look at the variable tab, execute the program step by step. So 36, which is 54 in decimal, is copied to W register, and once again if you click on it, so 58 in decimal is 3A in hex. Okay, and next keep looking at the data memory map here now, and click next, execute the next instruction. So you can find 35, location 35 has the memory, and has the value 3A now, and 3A was the result of the addition. So this is how you can write small programs. This is how you can write an assembly program in MPLAB X, and you can simulate using the debugger, and you can watch the variables. You can look at the program memory, and you can also look at the file registers, which is the data memory. Stop the debugger. Before you close the program, stop the debugger. So follow the same steps to complete the activities for this lab, and submit the program code. Submit the program code in a text file. Submit the program code in a text file, and you can take the screenshot using this. You can take a screenshot of this area, the file registers and the variable tab. You can take screenshots of the file registers and the variable tab as the result of your activity, and you can submit them along with the program code in the assignment. To submit the activity for any lab, click on the name of the lab itself. For example, if you click on this title of the lab, it will open the assignment submission for that particular lab. One more important concept that you must know, and you must be able to solve
without using a calculator quickly, just from your own memory, is how to convert hex numbers to binary numbers. You may have already studied this before in previous courses, but now you must be able to immediately convert any hex number to its equivalent binary number. So for example, if you are given the number 0x28, how do you write this in binary number? So immediately by looking at the numbers, you should be able to understand that number 2 is 0010 and 8 is 1000. So similarly, if you have 5a, for example, then 5 is 0101 and a is 1010. So you should be able to do it really fast just by looking at the numbers without using a calculator. So 7 is 0111 and 4 is 0100. And similarly, if you have, for example, BD 1011 and 1101, for example, E3 is 1110 and 3 is 0011. So any given number, you should be able to solve it and you should be able to convert it into hex numbers really fast. And same way, if you are given binary numbers, you should be able to convert those binary numbers into hex numbers. So for example, if you have a number like this, what is this number? So you should be able to immediately say that this number is 0x1f, and let's say if you have a number, now this number is 0x8 and 6. So whatever number is given, during the quizzes and during the exams, you will not have sufficient time to use a calculator to convert hex numbers to binary numbers or binary numbers to hex numbers. So practice this as much as possible. Practice this, and this will be useful for you in your future lab activities and quizzes. So this is all for lab 1. Complete the activities and you can submit it on Blackboard. And if you have any questions or any doubts, you can post them on the Blackboard discussion forum. Okay, wassalamu alaikum wa rahmatullahi wa barakatuh. Subhanallah wa bihamdihi, subhanakallahumma wa bihamdika, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilayk.